Hi there. This is a broadcast for meteorology students at Floyd Central High School, dual credit course, and our goal here is to focus on the atmospheric moisture and stability in a more condensed form. More specifically, we need to focus on absolute humidity, specific humidity, and vapor pressure. These are three terms that are historically quite confusing in Chapter 4. That's why we spend 2 weeks on Chapter 4, because we introduce a skew-T chart. We overlap that with a different type of psychrometric chart that students are hopefully familiar with, called dew point relative humidity, and those are terms that are at the bottom of the list that are hopefully not as confusing. So we're going to look at 10 slides here in brief, and I want to cover with a different perspective the top three items on this bulleted list, which is absolute humidity, specific humidity, and vapor pressure. So a quick review over atmospheric moisture. Make sure we can understand the water molecule anatomy. It looks like a Mickey Mouse here. We have 105-degree separation. It is a polar molecule, and that means it has some unique properties that hopefully you can recall studying in biology. This makes a strong physiological connection to the water molecule and its processes that allows us to transport materials, to be able to distribute easily, to be able to withstand the downward pull of gravity, so on and so forth. So it does have a 105-degree separation between the two hydrogens, and the oxygen has a slightly negative charge compared to the hydrogen, but it does have the appearance that most people can hold on to that looks like a Mickey Mouse ear, and that is intentional. When we put those together and we start to change their state, what that gives us is a latticing-like effect, where we have a process that is a hexagonal formation, and this is the backbone of crystallization. So whenever we really start to reduce the temperature atmospherically, we all know we have a snow or frozen precipitations, and those frozen precipitations have to have some form, some backbone, and that is what is projected by this type of configuration. So an ice crystal, which is literally billions of molecules, and we'll talk about that a little bit later in a different slide presentation, but that is going to be a important concept to understand. So when we talk about molecules of water, and we're into a snow crystal or a water droplet or a cloud droplet, we're into the billions of these. So it takes an amazing amount for these atmospheric processes that we take for granted to truly occur. So let's go into saturation. Hopefully you've got this by now. If something is saturated, can you tell me what percent it would be? Hopefully 100% pops into your mind. So think of something like a saturated sponge. One drop in, not until one drop comes out. That's what we're getting to here. So let's look at an example of a container. When we have condensation that is meeting evaporation, in other words, one molecule of water is condensed when one molecule of water is evaporated. Once we have that balance, then we are considering saturation. It is expressed numerically as 100%, and that is what we determine with our common vernacular when we say saturation or humidity. So when it's humid, what we're talking about is the balancing between condensation and evaporation. And what we're talking about in specific during this presentation, during this lecture presentation, is going to be water. And that's what we'll continually refer back to. Condensation, that is where we have a slowing of energy, specifically kinetic energy of the air. And what we have in the right side here is warm air. And warm air is able to move around quite rapidly. And that warm air is able to continue to expand or continue to move in directions and move quickly away. So what we have is high levels of kinetic energy, and that warm air is able to stay away from this nucleus. And that nucleus being things that are called condensation nuclei in the atmosphere. We will talk about those most specifically in the chapter relates to cloud formation. But right now, think of that as a surface, a tabletop, a chair, if you will. And what that deals with is a surface that allows water to land on. But water is not going to set down, not going to settle unless it loses what? Hopefully you thought of kinetic energy. So if we move into the next portion of this slide, what we have is a sample of cool air. Notice that this molecule of this nuclei right here, that nuclei is still present, but look at how the water is setting down. Why is it setting down? Because of less kinetic energy. Why was it not able to settle in the warm air sample? We had more energy that is allowing the water to move quicker. So we have a greater expansion. We can have relationships to pressure there. But right now, if you can get this type of an image or imagery in your mind, then you've got the idea of condensation and why we have condensation. So this is exactly why we have condensation of moisture upon glass, upon windows, upon mirrors, upon materials in the atmosphere. It's just that it's arbitrary to us because we can't see the materials in the atmosphere, and that's what we'll have to struggle through in the next couple chapters. Atmospheric water circulation. This is our water cycle, except it's enhanced. So let's make sure we can understand a few things here. For example, infiltration. Make sure we can connect to that. That was in a previous presentation. Evapotranspiration is hopefully something you can remember from biology. Evaporation you've got. Sublimation was something we're bringing forward from chapters 2 and 3. And then don't forget about our groundwater discharge. We do have things, aquifers, water tables, our springs, artesian springs, so on and so forth. And those are things that happen under the ground, under our feet. We forget about that, but that's a major source of drinking water for most of the planet. We do have our traditional precipitation, and we should understand that we have precipitative values that are unequal on the planet, and our runoff is unequal as well. We have areas that are collection basins, and we have areas where we don't have the capacity to hold that very well. So when we see these processes, do make sure you have the traditional water cycle down, but also make sure you can go into a little bit greater detail of the items that are enhanced, the items that are highlighted on the screen. All right, let's dive into humidity. Here's where it gets a little confusing. Let's think about humidity as just the focus of water vapor. So in this section, we're going to concentrate our focus on water vapor. That water vapor is this Mickey Mouse here that we looked at earlier. Okay, so within this air parcel, what we have is water vapor. We need to communicate in society for different reasons about water vapor. It's humidity in general, but as we have a greater understanding of this process, we have a greater application of knowledge, and we might need a little bit better way to communicate. So how do we use that? Well, there's 3 or 4 ways that unfortunately get confusing. And one of the ways that we talk most about in regards to humidity in the atmosphere is relative humidity. Relative humidity gets kicked around a lot in broadcast. And when we talk about relative humidity, we use percentages. So when we say that it's 70% or 80% relative humidity, it makes sense to us. It's tangible. However, it's one of the forms of relative humidity communication that we understand the least. We get the most confused with relative humidity, and that will become apparent as we move through the slides. So let's move into this. When we talk about water vapor content inside this parcel, it can be expressed in a couple of different ways. We're going to start first with absolute humidity. Absolute humidity is a focus upon the amount of water to a volume of air. This can present some problems, and I think they'll become quite apparent when you look at this illustration. Notice the volume of air in the lower illustration. The volume of air is defined by the circle perimeter. When we allow the air to rise or consider the air rising, then the air parcel is able to expand. Why? Less pressure. Remember that from chapter 1, 2. When we talk about moving away from the Earth's surface, this air parcel is able to expand out. So what does that mean about water vapor? Well, it's a bit misleading, because if I don't add or subtract water vapor into that parcel of air, and I just want to communicate about the parcel of air, then if I live in one part of the planet versus another part of the planet, even though I'm talking about the same air mass, my communication and my data is going to be a little different. So those people that may live around sea level, around this line at the bottom of a mountain, might be talking about the exact same amount of humidity as people that could be well above sea level at the top of a mountain, which would be an extreme case. But to get the point across, what we're saying is we could be dealing with the exact same humidity in an air parcel and have entirely different values. So let's try these. 3 questions to check your understanding. Does the amount of moisture in the parcel change as it rises? No. We didn't talk about adding through evaporation. We didn't talk about removing through condensation. There's no clouds here. We're just saying we're just allowing the air. Absolute humidity would have to do what as altitude increases? Because there's more space, would you drop your humidity value or would you raise your humidity value? it would have to be dropped. There's more space. Therefore, the area looks more cavernous. And if we have more space in a house, if we have more space in a room, we typically like to fill it. Therefore, our volume would be the larger of the two, but our value of relative humidity would move down. So is absolute humidity a good moisture variable? Unfortunately, it's not the best. So we don't hear about this a lot, but we do have an application to it. Specific humidity is a little different. When we have specific humidity, we're talking about the mass of water vapor to the total mass of air. Now let's consider this sample we looked at before. Those Mickey Mouse ears were water vapor. Now let's consider the other things within this as well. We have nitrogen in green, and then we have oxygen that represents the red here. So when we're talking about the mass of water vapor to the total mass of air, we become a little bit more accurate with our discussions. For example, in a given partial, we might have 2 grams of water vapor. However, we might have 2 kilograms of all other gases. Therefore, the specific humidity becomes 2 grams per kilogram. And that allows us to speak very carefully about what it is in the atmosphere that relates to water. So ultimately, it doesn't matter if this partial does what the other did. When it rises, if the partial expands, because we're not concerned with the areas in between. We're not relating it to volume. We're relating it to comparison. So even if there is more space in between each one of these molecules, it really doesn't matter because we're talking about the mass of water compared to the total mass of everything else. So if that mass of water is in a space that's 3 to 4 to 5 times as big, it will not change. So it's a nice view of the water vapor. So specific humidity is pretty useful for those things. Specific humidity can also be approximated, and we're going to see that in regards to an upcoming. Now let's try this. What will a latitude being lines like the equator on the Earth, what will the latitudinal distribution of specific humidity look like? In other words, where will the greatest specific humidity be if we understand that we're just talking about the mass of water vapor to the total mass of air? Would it be at the equator or be at the poles? If it's total mass, what we're looking for is the greatest mass being next to the most humid environment. And that would certainly have to be the equator. So then the equator has the greatest amount of specific humidity. The poles, specifically North Pole, has the least amount of specific humidity. Mid-latitudes would be in between. So hopefully that makes sense in regards to specific humidity. Now mixing ratio. Mixing ratio gets a bit more specific, and we can use specific humidity to approximate mixing ratio, but this does have an application. We will use this in class as practice as well. What we do here is the mass of water vapor again, except this time we're talking about the mass of dry air. We're not concerned about air that is humid. So what do we mean by dry air? Very low relative humidities. Air that might produce a nosebleed, air that might produce an indoor environment that would be conducive to fire. It's too dry, very low. This would be a wildfire type of a condition. This would be where we would issue burn bans, where we would be very concerned about a drying wind because it's sinking in the atmosphere. So when we're talking about just dry air and mixing ratio, then we get into that type of analogy. So here we are, we're talking about water vapor, and we're talking about the air that's dry. So how do you know that you're looking at a dry air mass here? We would have to understand a little bit about what associates value to dry air. So when we're talking about the idea of a mixing ratio, formally it's the ratio of mass of a variable constituent in the air, which for us, our variable constituent is water vapor. Remember, it changes from 0 to 4% to the mass of dry air. So when we talk about mixing ratio, we're talking about water vapor, especially in humidity, dealing with chapter 4. Most of the time, as you move on, you might deal with this. And if it is talking about a mixing ratio in another application, engineering course, whatever the case may be down the road, it would be duly noted that it's not water vapor, or that may be something else. For most purposes, the mixing ratio is going to be approximated by the specific humidity, which we talked about last, mass to mass. So when we look at those, we can have some correlation. But if we need a more specific value, we're going to go with mixing ratio. So let's look at this. When we have a partial where the mass of water vapor is 1 gram, but the mass of dry air is 1 gram or 1 kilogram, then we have a 1 gram per kilogram, which was less than what we had with our specific humidity, because this specific humidity did not take into account just dry air. Then the mixing ratio has a slightly different value there. So hopefully that helps alleviate any type of confusion over that. Vapor pressure is a form of partial pressure. So remember what we did in the second week of the course. Early on, we dealt with the idea of a partial pressure. You converted partial pressures of oxygen from Pikes Peak or Mount McKinley. You did an outstanding job with that. This is the same type of form, or same type of line of thought here, except we're vapor pressure. So what would vapor be in the atmosphere? Hopefully you're thinking of water vapor. So given a partial of air comprised only of nitrogen, oxygen, and water vapor, what we can do is just focus on water vapor. Just like what you did earlier in the course with nitrogen, oxygen, you told me that when we had 1,000 millibars of total atmospheric pressure, nitrogen was 780. Therefore, when we say vapor pressure is just focusing on water. And because water is in this sample 1%, then we should be able to ask ourselves, if we're figuring what the vapor pressure is, what is 1% of 1,000? That would give us our vapor pressure that we would use. So this is a form of partial pressure, and that's what we get into is a sum of pressures, but in parts. And what we're after is the part of vapor pressure. So that'll conclude what we're focusing on today. Hopefully that makes sense. These are things that have been in the past confusing. They are a part of this this chapter that you're in, and many of you will see those terms down the road, especially if you take a technical track and you get into a 4-year institution and you're going to be dealing with these types of problems. They're very good reinforcement of multiple areas within physics and engineering. Sometimes architecture will use these types of things because of the indoor quality of air and those types of concerns with building materials as well. So if you have any questions, feel free to ask those in class. We will reinforce this, and you'll have 3 points of contact with this information. So this is our second presentation. We'll have a practice set in class that we'll have with guidance. And by all means, ask if you have questions. And I'll see you in class. Thanks for